Let me explain what I mean by making a simple circuit look not so simple. Just watch. So this is where the current enters. And this is where it is leaving, and you have to find the resistance of the circuit. It's quite simple. These two resistances are in parallel. We'll call it as R1, R2, say this point C, and R3. R1 and R2 are in parallel, and then that combination of R1 and R2 parallel is in series with R3. Quite simple to solve. So your answer would be, now imagine these resistances were actually with you, and what happens is this part over here, this part breaks off, and how would it look like? It becomes something like this. So you see that this part is broken off, and you want to do a repair job over here. Now to repair it, you have to join this to this. You can use a small wire to join it. You can pull this to this point. Pull this point, broken point. I'll call this broken point as C dash. It has broken from C. So you can pull the C dash point and join it to C, or you can join it with a wire. Now suppose I have a wire with me with insulations removed at the ends, but it's too long and I'm too lazy to cut a short wire and join it. So what I do is I take that long wire and join the two broken off points. So will it not serve the purpose? Yes, it will serve the purpose. Wires we are considering as ideal, so this won't have any resistance, and it's the same, the circuit is same as the earlier circuit. Now let me present this circuit in a slightly different way. I start pulling this end such that this curved wire becomes straighter. So now the circuit is like this, and I still pull it a little more, a little more, a little more. I tend to make this flat over here. So see how it will look like. So what I've done is I've made this resistance R2 flat over here, and the C dash point has come over here, and they were joined by the pink wire, this curved long wire, which now I'm going to make it edgy and straight. So that's your circuit now. Now this circuit and this circuit are the same circuit. If asked to solve, you might get little confused in identifying that this R1 is in parallel to R2. If the circuit was originally given like this, our aim is to work back and make this circuit look like that. So what we need to do is, first thing is identify the long wire which is not necessary. So in this circuit, clearly this is a long wire which is not necessary to be that long, and this is what we have to work on. These edges also you can smoothen them out so that in your mind you're more clear on how to make them short. Now you have to somehow entwine, you have to take this wire, entwine it such that this resistance curves and curves. You keep entwining and pinch This has curved over here, and then you have to pinch the long wire over here. This long wire becomes a point wire. This long wire, you have to shorten it in your mind, and think of it as a shorter wire. Like over here, that long wire is a short wire like this. Here also think of a shorter wire like that. Again, this long is not required. Think of a shorter wire. I'll make the shorter wire in yellow. Shorter wire like that. Long wire is not required. Hence, this one looks as good as this one. So we'll practice a couple of more questions and give you a quiz on this. So this is the problem in hand. We have to find the resistance between this point A and this point B. The current is coming from here, taking various paths and going out from B. So we have to identify what's the resistance between A and B. Suppose all the resistances are having the same value, say 2 ohms. Take a minute, solve it. You may pause the video. Now, two things I'm asking you to look out for: edges and long wires which are not necessary to be that long. So where are the edges which can be smoothened? Now this is one edge which can be made smoother. This is an edge, and the long wire, more importantly the long wire, this is the long wire which need not be that long. So what we need to do is we have to make this wire smooth, curvy, this wire curvy, and entwine this wire. You have to entwine this and you have to bring it to a point. You have to pinch it. So how will it look like? So I'll keep this resistance where it is and try to, and while I'm entwining this wire, this will curve and this point A will come nearer to this point. So I've worked on this edge, I've worked on that edge, and this wire has become shorter. I'll make it still shorter such that I have a better feeling of how the current is flowing, and I have a better understanding of what all resistances are in parallel and series. Now before you do that, you may go ahead and simplify the parts you have already identified, like these two are definitely in series and these two are definitely in series, so you can make those two resistances as a single one and shorten this. So what we'll have now is these two as a single resistance. So a new resistance, I'll draw that in pink, and this wire over here which are joining to this needs to be shortened still more. This point, say this point A, that was the exit point B. Those two resistances also you have made as single, and this is what you get. You may further shorten it, and I hope it is clear now that the three wires are in parallel. The three resistances now are in parallel. Let's try out one more. So that's my basic frame. Let me throw in some resistance, some resistors. So here is one. So nothing is going directly to B. Let me put one here, one here, one here, one here, say one here, one here, and one here. Yeah, that's pretty much. Do I have a direct route from A to B? No, I got a resistance here, I got a resistance there. No, I can't go directly to B. If I could go directly from A to B, it would have been a zero resistance circuit, because As I told you before, the net resistance of the circuit is lesser than the least resistive root. So there is no zero resistive root over here, so resistance won't be zero. There is always you encounter resistance whichever way you go. Let me put one more over here. Now how to solve these? These are having a lot of long wires which were not necessary to be that long, like this one over here. If I just entwine it into one single thing over there, and this point also comes to that point, clearly these two would be in parallel. These two, if I have entwined this over here, those two will be in parallel. So I don't have to go for the whole circuit together. I can figure out which resistances are in parallel and make them as one. If I put them together, I put one resistance in between. I put one resistance instead of these two. Instead of these two, I can put one resistance over there. They are clearly in parallel because this point over here and that point over here are same potential. They are equipotential points. These 2 points are same potential, so they are in parallel. In fact, this point and this point is also same potential, so they are in parallel. So a lot of things which are in parallel, and once you have put an equivalent resistance of those parallel ones, you'll find out the things which are in series. So if you go one by one, it will be easier for you. I can't make all the circuit diagrams. So what I'll do is I'll tell you one other way of doing it, which is identifying all the equipotential points and then redrawing the circuit, and most probably you'll get the answer in one go. In this case you will. Other cases you might require to again do the same exercise, and you'll get in few steps. So identifying the equipotential points, meaning to say, as we have done earlier when we started this part of the lesson, so the equipotential points are the points which are electrically the same, they don't have a potential difference. So say A, what other critical points in this diagram is same as A? Let me just imagine how the current will go. The current wants to go from A to B. It's as if A is a uphill thing and B is down the hill, and water has to flow through all these routes, all these various routes. So current will just divide into 3 parts and will try to go to B. It could have gone directly to B from here to B, but there is a resistance, so it will check out the other routes also. Maybe this is a less resistive route, so more of the current will go in this way, but not all. There are other routes, and hence some current will choose to go from there. If you remember the movie hall ticket thing, so there was one route where a lot of persons were allowed, but there were other routes where 1 or 2 people could go through the door. So these are those routes. Now if the current is going from here along this wire, then all these points are equipotential points because there is no resistance from here to there, so there is no current drop. So all these points are A. I can't mark A all over, but on the critical points I'll mark A. So this is a critical point, I'll mark that as A. There's another critical point, I'll mark this as A. So if the current had taken this route, then all these points are also A. All these pink dots, all these pink points are A. So this is your A and no further, because it crosses a resistance, then the potential drops. It crosses a resistance, the current crosses a resistance, and the potential drop. It drops by amount of the current through the resistance into the resistance. That's the Ohm's law. So those are my A's. Now let me see B's from the other side. So this is my B, this is my B. So these points are all B, but then it will change. So no need to mark. This region is your B. This is some other potential over here. Current has come and it has dropped by a certain potential, and it has got a potential value less than A, but how much it is we don't know. Let me mark this as C. So what all points you think are C? So from here, wherever the current is flowing in whichever direction, there is no resistance in all these routes, all these yellow routes, all these yellow points. From wherever to wherever I can flow without encountering a resistance are C. All these points are C. So let me mark the critical ones as C. These are all C. And then what is this? There's a new point. There is a potential drop from C across this resistance to, say, call it as D. D is a new point. All these purple points are D's. Now to solve the circuit, as I told you before, you can take two resistances at a time and replace it with one. What I mean is like these two. I'll number the resistances. Say this is number 1, this is number 2, this is number 3, this is number 4, this is number 5, this is number 6, 7, 8, 9. I'm pretty sure 2 and 3 are in parallel and I can't imagine the other ones properly. So what I do is I replace 2 and 3 with a single resistance. The setup over there is something like this. That's your 2. That's your 3. Just pinch these 2 points into one, pinch those 2 points into one, and it will look like a curve over there, and instead of the 2, replace it with the equivalent resistance. So if both were 2 ohms, this equivalent resistance will be 1 ohm. And do away with this, do away with this. So if you keep doing that, you're going to simplify your circuit. But I'll do it in one go because I can draw all the simplified ones. So let me put all the critical points over here. That's your A, that is one potential point, electrical potential. Then there is a C, let me draw it somewhere here. That's your C. Then we have a D also, so let me draw it over here. That's your D. You may draw it wherever you want, and then that's your B. Then check the resistances between A and B and draw all those resistances. Check the resistance between A and C, draw all those resistances. Check the resistance between C and D, draw all those resistances. Check the resistance between any 2 point and draw all those resistances. So let me see which is there between A and C. A and C. This first one is between A and C. So I'll draw that. Drawn. Then number 2 is also between A and C. So between A and C, I've drawn this. Number 3 is also between A and C. Now no longer I feel whether this is in parallel to 1 or not, because I've identified the potential points and I'm just going by that. If you would have simplified and curved it and make the long wire shorter, you would have seen how 1 is in parallel to 3 yourself. But that is for you to do yourself. So that's my number 3. Number 1, number 2, number 3. What about number 5? Number 5 is also between A and C. You see this wire over here was actually, if pinched, it was over here. So 5 would have come over here between these 2 points, and these all points are pinched into one. So that's your number 5. What else is between A and C? So I've drawn 3, I've drawn 5, I've drawn 1, 2, 3, 4 resistances. 1, 2, 3, 4. A and C, nothing else. I've got one more between A and C. Number 6 is between A and C. So again you could have seen that if A is over here, 6 would have been like this coming to C. So number 6, I've drawn that. Now let me see what all between C and D. C and D, the original one, I would say. That's your number 7. Then this number 8 is also between C and D. This point was in fact this point. They were all same. This pinched over here, and then that long wire just this resistance curves and comes over here. That is number 8 between C and D. So we have drawn all 1, 2, 3. Number 4 is missing. Number 4 is yet to be drawn, and number 9 is missing. So between D and B is number 9. So that's my number 9. And between A and B is number 4. Number 4. So that's your circuit. I hope you can do it now. All these resistances 1, 2, 3, 5 and 6 will become a single resistance from A to C, the value of which would be, if all the resistances are same, say R, then it would be 1, 2, 3, 4, 5. It would be R by 5. What about this? It would be R by 2. So R by 5 plus R by 2 plus R, they would be in series. This part R by 5 would be in series with this, which will be R by 2, would be in series with this, which is R, and the 3 which are in series would be in parallel with this, with R. So your circuit would be R by 5, R by 2, R and R. So taking LCM over here as 10, this would be 2 plus 5 plus 10, which is 17 by 10 R in parallel with R. That's your 17 by 10. So 17 by 10 R in parallel with R comes down to 17 by 27 R. That's your final answer between A and B. That is what you finally get. Let me just have a very quick cross verification. I only know that my answer should have been less than R. Why less than R? Because my shortest route from A to B was having just resistance R. So any other route is a extra route, and hence it's going to ease off the flow from A to B. So the current will not only choose this easiest path, some of it will go from the other parts and will make the flow easier, or more than, the flow will become more than had this resistance number 4 just have been there. It had been just number 4 over there and no other resistances. Then it would have been more resistive. The circuit would have been more resistive. Adding so many resistance, a bunch of them all around it, has in fact reduced the resistance, because all of them are providing extra paths which are called parallel paths. So is my resistance coming less than R? Yes, it is coming less than R. 17 by 27 R is a fraction of R. It's less than R. So most probably it would be right. So I hope it is right. I hope you are ready to tackle some quiz on resolving circuits.